This is a video example of how to use Coulomb's law to find the net force for particles in a plane. Here's the problem. I've got a 5 nanocoulomb particle and a 6 nanocoulomb particle and a negative 3 nanocoulomb particle. And I want to find the net electrostatic force on the corner particle, that's the 5 nanocoulomb particle. The first thing I need to do to solve this is to find or create a free body diagram of all the forces acting on the 5 nanocoulomb particle in the corner. The 5 and the 6 are the same sign, so they will be repelled apart. The 6 will move to the right, the 5 will move to the left. Since the question asks about the 5, I'm going to ignore what happens to the 6 and just pay attention to the 5's motion. So the dot where the 5 nanocoulomb charge is, I'm going to make that the body, the free body, and there's my first force up there. Force of 6 on 5. The 5 and the negative 3 are oppositely charges, so they will be attracted towards each other. Since the question asks about the 5, I'm going to focus on just what the 5 does, and it will move down towards the negative 3. Now, in an instant later, they'll be in different positions, but I don't care about that. I only care about this instant in time. So now in the corner particle, I've made that my free body diagram, with a force going to the left and a force going down. To find the magnitude of the two forces, it's electric charges that are interacting with each other. So I'm going to use Coulomb's law, kq1 q2 over r squared. I'll find the magnitude of these two vectors using Coulomb's law, and I get 8.99 times 10 to the 9, 5 times 10 to the negative 9 coulombs. So it's a nanocoulomb, that's the n, and I'll replace the n with 10 to the negative 9. And the other one is 6 times 10 to the negative 9, and again I'll replace the n, the nano, with 10 to the negative 9. So it's all set, and there's my answer, 2.996 times to the negative 6 newtons. For the force of negative 3 on 5, I'll do the same set of calculations, and I'll get 1.3485 times 10 to the negative 9 newtons. So I've got the two legs of my triangle. I've just got to put them together, tip to tail, and draw my triangle. So here's my solutions triangle. I've got the horizontal vector, and then I've got the vector of f3, negative 3 on 5, and that's going down, and they're connected tip to tail. The resultant is the net force, and theta goes where the two tails are meeting. So that'll be magnitude for F net, and the angle will be the direction. To find those two values, I'm going to use Pythagorean's theorem to find the length of the hypotenuse, which will be the magnitude of the net force. So a squared plus b squared is equal to c squared. When I put in the numbers for the legs of the triangle, I get a final F net to be 1.38 times 10 to the negative 5 newtons. That's the magnitude. And the direction is found using trig. Tangent theta is equal to opposite over adjacent, so that's tangent theta is equal to 1.345 or 1.3485 times 10 to the negative 5 newtons divided by 299,666 repeating times 10 to the negative 6 newtons. And when I take the arctangent of this, I get 77.5 degrees. So there's magnitude and direction.